So let's continue with this and find IY. So now we're going to have a situation where we need to look at a differential element dx here. So IY equals the integral x squared dA equals the integral. So now we're going from minus b over 2 to b over 2. So we're starting here in this corner and we're integrating this way. We're adding up all of these lengths here of dx. So this is going to be x squared, and our dA now is going to be h times dx is our section. So h integral of minus b over 2 to b over 2 of x squared dx equals, let's bring it down here, and so we're going to get the same sort of thing as before, but now we're going to have h b cubed over 12 if you solve that. Okay, and we can go further and we can say, so the polar moment of inertia, which would be about this point essentially. Polar moment of inertia is JC equals IX plus IY. This is going to equal 1/12 BH times h squared plus b squared. I got that just by adding IX plus IY together. Okay, so what about other moments of inertia? What about the moment of inertia about the base of our rectangle? So moment of inertia about this. Well, we can calculate that too. I about the base equals the integral of y squared dA equals. So this time, since all of our area is above that, we're going to go from 0 to h. So we'll go from 0 to h of y squared dA equals the integral from 0 to h of y squared. Again, we're going to have drew a little picture over here to the left, and we can see that our d area is b times dy. So this equals b times the integral z to h of y squared dy equals b times y cubed over 3 evaluated from 0 to h equals bh cubed over 3. So note we can also get this by using a relationship called the parallel axis theorem. I'll derive this in a second, but let me just display it. So I about the x-axis here, or about any axis, essentially equals the centroidal moment of inertia, or the moment of inertia about the centroid. And so this is not the same x over here. This would be a different x. So it'll be the distance to the centroid plus some area times d squared plus the area times d squared, the distance to the axis. So in other words, we could take bhq over 12, the moment of inertia about the centroid for our rectangle, and then add the area b times h of our rectangle, and then multiply that by the distance from the centroid to the new axis that we are taking our moment of inertia about here, and that distance is h over 2, and then we square that. So I guess I wasn't recording. So here the distance h over 2 is this distance d here from the centroid, measured from the centroid. So we get bh cubed over 12, which was the moment of inertia about the centroidal x-axis, and then we add this, calculate this as bh cubed over 4. Simplifying, we end up with bh cubed over 3 is what we calculated up here, which is what it should be. So let's now derive the parallel axis theorem. So let's start with a general mass that is at, here is our center, we'll call this x prime, and this our y prime. That's our center of gravity of the mass. So there is then some distance from here to here of d. I'm going to call that d1, but that'll be the distance in the y direction. From there, we will have a y prime distance to this, and from the centroidal axis, and an x prime distance to this. So now we got our axes in there. Let's go ahead and work this then. So I about the x-axis, that's this axis, of this is going to be equal to the integral of the distance to our differential elements squared, which will be d1 plus this y prime squared dA, and so this is all about a, and then so this quantity is squared here, so let's work that out. We've got y prime squared. Let's change the way I write that. Y prime squared plus 2 y prime d1 plus d1 squared, all times dA here. So Ix equals, split these up into individual integrals, y prime squared dA plus the integral. We can actually make this, since I want to analyze this, pull out the 2d1 and make this y prime dA plus the integral of, so we got d1 squared outside times dA, the integral of dA. Okay, well, on inspection, we see that this is just what we calculated before, I of x about this prime, which we'll call the centroid, I about the centroid axis. This is d1 squared times a, so this is d1 squared times a, the area, total area. So what is this? Then this is simple. So what are we doing here? We're taking a differential area and we're multiplying it by y, so we're finding the moment of some area about the centroidal x-axis, and then we multiply it by that factor. So let's think about this for a second. So if I took that whole area, all the dAs together into the whole area, and multiplied it by the centroidal axis, well, that doesn't compute because the distance from the centroid to the centroidal axis is 0. So this equals 0. And if we remember that this equals the sum of this, or equals the integral of essentially all these little dAs together, then this must equal that, and so it must be equal to 0. So this falls out of the relationship and equals 0. So likewise, we can do the same thing with y. So Iy equals I about the centroidal axis, the centroidal moment of inertia, plus the distance from the centroidal y-axis to the y-axis squared. That's what d2 is. So we're heading in the x direction now to the y-axis, and a is the same, a. So because ix squared plus iy squared equals j0 squared, we can do the same thing here. We can go j0 equals j bar c. So this is about the centroid plus the area times some distance squared. So that's distance to the centroid from O, the origin, or wherever we're taking that J0. All right. Okay, I'm just going to mention radius of gyration, which we represent with these K. So radius gyration sub x is the integral of Ix over A. And we can also look at this as Ix equals K sub x squared, A, the radius gyration squared. K sub y equals the integral of Iy over A equals Iy equals K sub y squared A. And finally, K0 is, as you might guess, J0 over A equals, or leads to, doesn't really equal, it leads to J0 equals K squared A. And that's it.